Welcome back for part 3 of section 7.1, which I'm hoping will be the last part, but okay, we'll see. In this section, we're going to take a look at finding the sample size required for a given margin of error E. All right, so let's look at the scenario of suppose that you are going to create the survey and gather the data, and you know that you're going to be making a confidence interval. So it's going to have a margin of error in it. And rather than just doing the survey and seeing what happens, suppose that you want to make sure that you get a margin of error that's within some given range that you're acceptable with. Like you want at most 2% or at most 5% or something like that. How will we go about doing that? Well, as we talked about earlier, the only variable in the margin of error formula that we have control over is n. So with a little bit of algebra, could we take that formula and solve it for n? Meaning, could I do some algebra on this where I would get n equals whatever with p hats and q hats and z's in it over there that would allow me to then know how big my sample needs to be to make this happen, right? So let's take a look at doing that algebra real quick, okay? So I want to solve for n. So the first thing I'm going to do is I'm going to divide by that z-score. So I'm going to have E divided by my z-score, my critical value there, alpha divided by 2, is equal to that square root of p hat q hat over n. Then I'll square both sides. So I'm going to get E over that z sub, I'm just going to call it z sub c rather than writing that alpha over 2 squared equals p hat q hat over n. So then I've got a statement where a fraction is equal to a fraction. So I'm just going to flip both sides. So that's going to give me n divided by p hat. Q hat is equal to the quantity z of alpha over 2 divided by e squared. And then I'll multiply both sides by that, which is going to give me a final statement of n equals p hat q hat times z sub alpha over 2 divided by e squared. And now I've got a formula that if you can give me this information, I can tell you how big your sample needs to be to make that happen. So if you wanted a margin of error of at most 2%, you'd put a 0.02 there. You'd put the proper z critical value there, probably a 1.96 if you're looking at a 95% confidence interval. But I know what you're thinking. But Brian, how will I know those if I don't run the survey? How do I get a sample proportion for success p hat and a sample proportion for failure q hat if I don't run the survey first? You're right, you won't. So what you could do is you could estimate those based on previous data, or you go with the worst case scenario of 0.5 and 0.5 for both of them, because when you make them both 0.5, it makes the product of p hat and q hat as large as possible, which would then give you the largest sample size or that would be necessary. Okay? All right, so one thing you want to keep in mind here is that what we're doing is we're looking at controlling the one thing we actually can't control, that is our sample size. And we know that when our sample size gets larger, our margin of error gets smaller. So if you can work backwards from a margin of error, you should be able to get a sample size. Let's take a look at what it would look like in application. Okay? So when the textbook author was conducting research for this chapter, he could find information about the percentage of adults who make online purchases. So he was looking for this, couldn't find it, but that information is important. And so how many adults must be surveyed if he wanted to build a 95% confidence interval that was off by no more than 3%. So the authors have decided they're going to conduct their own survey. And they want to know how many people to talk to. Well, I've got a formula for that now. I know that my sample size should be p hat q hat times z sub alpha over 2 divided by my margin of error squared. And if I want my margin of error to be no more than 3 percentage points, I'll put 0.03. And if I know that I'm creating a 95% confidence interval, then that's my 1.96. And then what am I going to use for p hat? And what am I going to use for q hat? Well, in part A, we're going to assume that prior data showed us that p hat was 0.8, and then q hat was 0.2. And then in part B, we're going to assume we have no prior information, so we'll go with worst case scenario of 0.5 and 0.5. So in part A, n's going to be 0.8 times 0.2 times 1.96 divided by 0.03 squared. So 0.8 times 0.2 times the quantity, 1.96 divided by 0.03, that quantity squared. And I get that we're looking at about 683 people. Well, that's an ugly n. 680. So if I have reason to believe that this is true, then all I need to do is survey 683 people, and I'll get a point estimate that will have a margin of error that is 3% or less. Well, that wasn't too bad. Let's take a look at part B. Part B says you have no prior data. So you're just going with the worst case scenario, which is going to give us the largest sample that we could possibly need. 0.5 times 0.5 times 1.96 divided by 0.03 squared. So 0.5 times 0.5 times the quantity, 1.96 divided by 0.03 raised to the second or squared. And I get we should talk to, it looks like about, what is that? 1,068. Now I know there's at least one person going, no, 0.111 rounds down to 1,067. Always round these things up. Because when you round them up, adding that extra person is going to make sure that you actually get that 3% or less. If I did 1,067, my margin of error would actually round to greater than 3%. So I'm adding an extra person, not really adding an extra person, but I'm rounding up to that extra person to make sure that I've got what I need. Okay? All right, let's look at some examples. So here are some problems where we're just going to be asked to do something. It might be find a confidence interval, find a point estimate, find a confidence level, whatever it's asking us to do, and we're just going to do it. Okay? All right, so we'll read the first one. The USA Today claims that 44% of those who access the internet read the international news online. You want to check the accuracy of their claim by surveying a random sample. Okay, so you are going to check the accuracy of that 44% by surveying a random sample of 120 adults. So you've got a 120 sample size, and you're going to ask them if they read the news online. 52 adults responded with a yes. That means that we have an X of 52. Our job is to use a 95% confidence level to test this newspaper's claim. So we're going to build a confidence interval, a 95% confidence level confidence interval, a 95% confidence interval, to test this claim. All right, so I know what a confidence interval is. I know that a confidence interval is a p hat plus or minus a margin of error. And I could work it out this way longhand, but I am going to argue that let's use the calculator to create this confidence interval. In order to use the calculator, I need to know three things. I need to know an n, which I've got right there, so that's good. I need to know an x, the number of yeses or successes that I got, and I got that, that's good. And I need to know my confidence level, my CL, and that's going to be 0.95, also stated in the problem. So I'm going to go over to my calculator, I'm going to go to my stats, my tests, and I'm looking for that one proportion z interval command. My x here is 52. My n here is 120. My confidence level is that 95%, 0.95. And I calculate, and I see that I'm looking at a p hat of 0.43. And I've got an interval, a confidence interval of from 34.5, if I go to one decimal place, percent to 52.2%. Right? If I needed to know E, if I wanted to know E, I remember how to do that. I'll take the top one, 0.522, minus the bottom one, 0.345, and divide that by 2. And I get that my E is about 8.9% if I needed it, right? All right, so now let's take a look. What do you think about the claim that was made by the USA Today? Is that 44%? Does our interval capture that? Well, yeah, 44% would be, our interval would catch 44%, it would be in there. So I'm going to say that, yeah, I think the USA Today's claim is pretty good. I've got a 95% chance of, if 44% is accurate, my interval, it's in my interval. My interval contains the value P. Yeah, so I would say that, yeah, my data backs it up. I feel pretty good about that. Right? All right. A survey of 300 fatal accidents showed that 123 were alcohol related. So I'm just going to stop right there. Boom, boom, I got some numbers. What is that, 300? That's our sample size. We had a survey. What's this, 123? Well, that's how many times we saw, and I hate to say it like this, that's how many times we saw success. I hate to think that a fatal accident is success, but that's what we're measuring, that's what we're counting, that's how success is defined. And we've got a confidence level of 0.98. We're going to construct a 98% confidence interval for the proportion of fatal accidents that were alcohol related. So of all 300 accidents where unfortunately someone died, 123 of them were alcohol related. What is the interval, confidence interval, at a 98% confidence level for the true proportion of fatal accidents that were alcohol related? This is a weird one, right? We don't see a lot of 98%ers. It's not one I have memorized, so I wouldn't even begin to try to use that formula. I'm just going to go straight to the calculator. So I'm going to go back to stat, over to tests. I'm going to find that one prop z interval. It needs an x, it needs an n, and it needs a confidence level. And I get that my confidence interval, first off, my p hat, my point estimate, is 0.41, or if you prefer, 41%. My confidence interval is 34.4% to 47.6%. And if I needed my margin of error E somewhere in the problem, like in the homework, if it was asking for an E in there, I know that I'm going to take the upper minus the lower and divide it by 2. So 47.6 minus 34.4, and I divide that by 2, and I see that trash man is driving by, sorry. I get a margin of error of 6.6%. So what is the population proportion of fatal accidents that were alcohol related? Well, I can say with a 98% confidence that the interval 34.4 to 47.6 should contain that value P. Okay. All right, moving on. You are running for political campaign. This is our last one. See 7.2 just showed up at the bottom there. You're running for political campaign and wish to estimate with a 95% confidence the proportion of registered voters who will vote for your candidate. Okay, so you're running a political campaign and you want to know what percent of the voters are going to vote for your candidate. Your estimate must be accurate within 3% of the true population proportion. Find that minimum sample size needed. Okay? So this is a minimum sample size. I know the formula. The formula says that n is p hat q hat times z sub alpha divided by 2 over margin of error, that quantity squared. And it looks like they want us to do this both ways again. One where we part 1 or A here where we don't know any information, and one where we do know some preliminary information. Okay? So in part 1, and I'll do 1 over here on the left, we're going to set p hat at 0.5. We're going to set q hat at 0.5, and our e is going to be 0.03. Our z sub alpha over 2 is going to be that 1.96 because of a 95%. And then we're going to say that n is whatever it works out to be. 0.5 times 0.5 times the quantity 1.96 divided by 0.03, end of quantity, square that quantity, and I get that we're looking at 1068. Hey, isn't that the same number we got earlier? Yeah, because if this is the same and this is the same, that's going to be the same for the worst case scenario. Now, what should be different than what we saw earlier is what we get for part B, or part 2, sorry, where we have an estimate of p hat at 0.31, which means q hat would be 0.69, and e is still 0.03, and z sub alpha divided by 2, our critical value, is still 1.96. Now what's n going to be? This is the one where it'll be different. So 0.31 times 0.69 times the quantity, 1.96 divided by 0.03, and a quantity squared. And it looks like we should talk to 914 people. So if I want to get an accuracy of within 3% at a 95% confidence, I need to talk to 914 people at least. All right, that brings us to the end of section 7.1. Have a great day.